Hi, and welcome to Chapter 14 lecture videos. Dr. P here, and in this lecture, I think I'll first start with an overview of the chapter. So we'll go ahead and take a look at the stability of conjugated systems, and that'll be this lecture. And we'll look at some experimental evidence. And then we'll look at the explanation for the stability using molecular orbital theory. And it's good to review a little bit of molecular orbital theory because we'll be using it again in chapter 30, and again after that in chapter 15. Then we'll go ahead and take a look at some reactions, namely the addition of HBr to conjugated systems, conjugated dienes. So we'll look at two different versions, 1,2 and 1,4 addition to conjugated dienes. And then as we explore the mechanisms for these particular reactions, we'll look at the concepts of kinetic, if I could spell correctly, that's an E. Hold on here. Kinetic, K-I-N-E-T-I-C, that's better. Kinetic and thermodynamic reaction control. And then we'll wrap up looking at the Diels-Alder reaction. Which is a particular reaction involving dienes, conjugated dienes. So this lecture is going to deal with, so we'll say here lecture 1. This lecture is going to deal with the stability of conjugated systems. And then subsequent lectures will look at the different reactions, reaction control, and then the Diels-Alder reaction. And the Diels-Alder reaction is actually a good segue into chapter 30, pericyclic reactions, because it happens to be an example of a pericyclic reaction. That is a cycloaddition. All right, so let's take a look at conjugated compounds and their stability. So, conjugation. Conjugation is simply alternating single and double bonds. Or let's focus on the double bonds. So double and single bonds. So we could have a conjugated diene here. So I've got alternating single bond with two double bonds. So double, single, double. Okay. I could have something like a, I often draw it like this. This would be a conjugated aldehyde. We could, have a ketone here. It's the CC double bond is conjugated with a CO double bond. Now, we'll look at this stuff later. we've looked a little bit at, well, actually no, we haven't really looked at conjugate addition, but we'll look at this later on this semester. But for now, let's focus on the conjugated diene. And I want to compare these. We have conjugated. We have isolated. And then we have, it's a little bit easier for these sp hybridized things to write in the atom there, cumulated. And of these, it's the conjugated that shows increased stability. Okay, so let's take a look at some ways in which our conjugated species is more stable. All right. I mean, it's all well and good for me to say, yeah, these are more stable, but, you know, maybe a little background of, you know, how exactly the stability was measured. If we looked at the hydrogenation of 1,4-pentadiene, which is this guy here, and compared it to the hydrogenation of 1,3-pentadiene, our enthalpy values here, or delta H naught I should say, are minus 254 kilojoules per mole and minus 239 kilojoules per mole. So that means that our conjugated species, let's see, conjugated is more stable. Oh gosh, not spelling good today. By approximately, what's the difference here? 15 kilojoules per mole. So that's the difference. So if we looked at an energy level diagram, this species is higher than this one because it releases more energy to get to the same place. There's some other interesting things too. What if we looked at an allylic system? Now, if we use NBS, we get bromination at the allylic position there. And if we use Br2, we would add here, but notice that with just NBS, we don't add here. So something's going on at this allylic position, given that it's right next to the double bond. So that's kind of interesting. Well, why don't we take a little break here and take a look at, before I actually start explaining how these things work. Let's look at some pictures of our dienes. All right. So if we have a conjugated diene, I could go ahead and draw, so here are my carbons, and these are my single bond, my sigma bonds, I should say, and then I've got a p orbital for each carbon, and let's see here, maybe I'll do pink and blue. So color these in, lobes, different phases. That's all that these are. They just indicate the phase of the orbital, because remember, these orbitals are wave functions. So like waves, they have orbitals. Now normally we would say that we've got overlap to form the pi bonds. And we could contrast this to, let's say, so this is our, that's that guy. And then let's do, oops, cumulated. So I got my carbon, carbon, carbon. So I'm not showing the hydrogens, of course. Now this middle carbon is sp hybridized. So it has 2 sp orbitals and then 2 leftover p orbitals. So what we end up with is overlap, but notice that these p orbitals are at right angles to each other. And then in our last system here, the isolated, I'll go ahead and have my p orbitals. Again, I'm not showing my sp orbitals, my sigma bond. So this has 2 hydrogens on it. So those aren't p orbitals, those are sp3 orbitals. And then I've got my overlap here to make these pi bonds. And make pi bonds there. Now notice that because these guys are close together, we could have overlap in the middle. So essentially the pi electrons are delocalized over the whole molecule. I have some models here to sort of show a little better than my not very great artwork. So let's go ahead and first let me show you the isolated. Let's see if I can get this in here. Hold on. Whoa, sorry about that. That's a little bright. Let me see if I can, the light is reflecting a little bit. Let's see if this does a little better. Yeah, I think that's a little better. There we go. All right, so I'm going to zoom out just a skosh here so we can see this a little better. So here is the isolated. So I've got my sp3 hybridized carbon in the middle, and my 2 pi bonds are isolated from each other. Now we'll compare that to the cumulated, where in order to get the 2 pi bonds, they have to be at right angles to each other, they have to be perpendicular to each other. So there's no overlap between this pi bond and this pi bond because they're in different planes, right? You can see that here. All right, so let me go ahead now and make the, just take a sec here. Let me make the, oops, I need to switch this around. Hold on a sec. Let's do, sorry, one of my model was not arranged quite as nicely as I had hoped. There we go, that's better. All right. So now here is the conjugated system. And you can see, so this is like what it looks like in the drawing, kind of end on. I've got p orbital, the spheres there, p orbital, another p orbital, and the 4th p orbital. And they overlap to give me pi bond and pi bond. But we could have additional overlap in between. There's nothing to stop us from having overlap here. And there. So this is what our system is going to look like. And it's this additional overlap that's going to lead to the stability of the system. Now, it's kind of all well and good for me to say, oh yeah, this overlap leads to stability, but we need a little bit better way of looking at it, and the way we do that is with molecular orbitals. So let's take a look then at molecular orbital theory. We'll say molecular orbital theory and stability. All right, let me zoom back in so you guys can see that a little better. And get that situated. There we go. That's pretty good. And okay. So what are molecular orbitals? Well, molecular orbitals are wave functions describing where the electrons are over a whole molecule. So as opposed to atomic orbitals, where we're looking at one atom and where its electrons are, we're looking at electrons delocalized over a whole molecule. Now, typically what we do is we take, let's do this, let's take two p orbitals, and then we can go ahead and combine these, and let me remove that plus, so I'll say and. And if we add them, we get one thing, and if we subtract them, we'll get another. So when we add them, similar phases will add. And so what we will end up with then, oops, that's the wrong pen, there we go. If we add them, we'll get our pi system. So this is a pi orbital. So we might just call it pi 1. Okay, so this is a molecular orbital. Those electrons are over the whole molecule. This example here would be something like CH2, CH2. I'm just focusing on the carbons. Now, if I subtract these from each other, I end up getting this kind of weird thing where I get you might think you would get zeros. Well, you do get zeros in the middle. And so there's an area here in the middle, which we call a node, which is 0 electron density. And we'll call this guy pi 2, but we're going to give it a little star here. And what the star means is that it doesn't contribute to bonding. So our pi 1 orbital is a bonding orbital. And our pi 2 star is what we call antibonding. Not only does it not contribute to bonding, it actively takes away from bonding. Now you may remember this if you go back and look at molecular orbitals of diatomic molecules back in Chem 1A. If you really want to dig around some of the lecture videos on my YouTube channel, you can look for those. Maybe I'll go ahead and put a link to those if you really want, but we're going to focus here on just the p orbitals and how they contribute to molecular orbitals. Because really the sigma bonds are best described as valence bond theory. All right, so for every atomic orbital we combine, we're going to get a molecular orbital. So if I've got 2 p orbitals, I'm going to get 2 molecular orbitals. All right, so now for the conjugated system. Well, what do we have? So I'm going to go ahead and put an energy axis here on the y-axis. And then what I'm going to do is I'm just going to draw a straight line, and I'm going to put in my orbitals here. Okay, so each of these is a p orbital. So what I have is, I've got C, 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 and then these are my p orbitals, right? Okay. So that's that stuff there. Now, if they all line up phase-wise, that is going to correspond to, or that is going to be, when we add all these guys up, we end up with that blob like this over the whole molecule, spread out over the whole molecule. And we're going to call that pi 1. And we'll fill in electrons in just a minute. So this is my energy level. I'm calling it pi 1. Now I can go up to the next energy level. And each time I go up, I'm going to introduce a node. So there's my node, the dotted line. And so where I've got a node, I have a phase change. So my phases switch. I go from blue to pink, and pink to blue. And this is pi 2. And this corresponds to the localized picture. Pi bond, sigma bond in the middle. Now I can keep going here. And I'm going to have 2 nodes now. And why not in the middle? Well, the nodes are going to end up being symmetric. There are mathematical reasons for that. I'll show you some of the math. Well, not really math, but when we look at the allylic systems, I'll go ahead and show you that, because allylic systems are a little different. And so this is pi 3. And then our last one up here, how do I know it's the last one? Well, I have 4 atomic orbitals, so I'm going to have 4 molecular orbitals. That's pi 4. Now, half of the orbitals are bonding and half are anti-bonding. So pi 3 is actually pi 3 star, and pi 4 is pi 4 star. And my phases are going to alternate with each orbital. And this is totally anti-bonding. It contributes nothing whatsoever to the bonding. Now, how many pi electrons do I have? Well, I have 2 here and 2 there, so 4. Let me go ahead and put those in. 1, 2, 3, 4. Now, I actually have a 0 of energy right here, so everything above this level is takes away from bonding. Everything below contributes to bonding. So I have 4 electrons in bonding orbitals, so I get a stable system. And it's this lower one here that explains the additional stability. Okay? An isolated, where's my isolated? Here's my isolated guy here. I'd have another atom in between with no p orbitals. So I'd really just be looking at these guys individually. And here, because they're not in the same plane, they can't overlap to give us this type of system. Now again, they don't actually look like this, they look more like these blobby things, but the way that we represent them is by drawing the individual component p orbitals. We call these we'll call these an LCAO. LCAO equals linear combination of atomic orbitals. And that's how we get pi molecular orbitals. We're just adding or subtracting them in different combinations. Okay. Now, I did want to talk about the allylic systems as well. So, you want to go ahead and watch this again. You want to be familiar with how I generated this kind of diagram. You'll want to be able to do that as well. We'll be doing this again later in this chapter when we talk about the Diels-Alder reaction, but also in chapter 30, and then again in chapter 15 when we talk about aromatic compounds. Okay, so let's go ahead then and take a look at MO theory and allylic systems. Okay, so let's go ahead and put our energy here. And let's look at the allylic cation first. Okay, now I'm not showing my, I'll put in my hydrogens, why not? So I have a p orbital here, and a p orbital. That's where the positive charge is. So I've got 3 p orbitals. So let me draw these in here. So I've got my 3 atoms. And I've got 1, 2, 3. Now I should end up with 3 molecular orbitals because I started with 3, and I've actually drawn the middle one incorrectly. And we'll get to that in just a minute. So I'm going to have pi 1, pi 2, and pi 3. Pi 3 is actually pi 3 star. So my pi 1 is going to be bonding. My pi 3 star is going to be anti-bonding. And my pi 2 is going to be non-bonding. Doesn't contribute or take away from bonding. Now remember, we talked about how we said this is resonance stabilized. Okay, I can go ahead and I can draw a resonance structure here. If I move my paper. H, C, H, C, H, double bond C, H, H. So I've simply put those electrons over there. I've got my positive charge there. And again, resonance is a man-made construct, so really it's a blend of these two is what's actually going on. So let's go ahead and take a look at what happens if we have, let me kind of keep that in the picture there. There we go. What if we have everything lined up the same phase? That is going to be our lowest energy orbital. Now what if we have one node? So our node is going to be right here in the middle. And so I'll just kind of black that in, scribble that out. It's just a dot. And there's no electron density there. And you're like, Dr. P, what happened? Well, let me show you that in just a minute. And then our highest energy here is going to have 2 nodes. and we'll alternate phase each one. And that's going to be our anti-bonding. So this guy's non-bonding because there's nothing in that middle there, so we're not going to add any to, it's not going to help stabilize things any. Now for our allylic cation, we have 2 pi electrons. They're in the double bond. No pi electrons here. So 1, 2. Well, there we go. That's why it's stable. We have 2 electrons, 2 pi electrons in the pi 1 bonding orbital. Boom. Nothing in the antibonding. Nothing in the non-bonding for that matter. Now, why do we get this? So if I added the following, I'm going to get, so really there's 2 ways to arrange this with one node. And making this a little small so that it fits in here. So let me just zoom in here real quick. So I could have my node between carbons 1 and 2 or between 2 and 3. So that's 2 possible ways I could do this to make my pi 2. Which is it? Well, it's actually an average of the 2. If I average these together, pink adds up to give me pink. Pink on this end adds up to give me pink. Blue adds to give me blue. Blue over here adds to give me blue. But now my blue and pink are opposite phase, so when I add them, they cancel each other out. Remember, these are wave functions, so they're opposite phases of the wave. You're adding sine waves of opposite phase, they cancel out. Blue and pink cancel, pink and blue cancel. We're left with nothing. So that is our null, our node. All right. So let me back up here again. Whoops, a little too far. There we go. Okay. Now, we could also have an allylic radical or an allylic anion. And these also have resonance structures. So here I could push an electron there, I could push one there, and push the other one there. Again, I'm doing single fish hooks here because I've got single electrons. And then my allylic anion has a lone pair and a negative charge. So I could push that over and push those electrons over. And that will give me my allylic anion system. Now if I go ahead and look at my, I'm not going to draw these because they're going to look the same. My orbitals look the same. But the number of electrons I have in each orbital is going to be different for the different systems. So in my allylic system, I have 1, 2, 3. I can put that in a p orbital. It doesn't have to be in an sp3 orbital. It could be in a p orbital and then delocalize. So I could have 1, 2, 3. So that guy doesn't contribute to bonding, but it doesn't take away either. And we actually see that, yes, this accounts for the reactivity at either end of an allylic radical. Same thing with the allylic anion. I've got 2, 4 pi electrons. 1, 2, 3, 4. So that accounts for what we observe with the resonance structure, or what we explain with the resonance structure, that we've got the negative charge delocalized on the two ends of the molecule. Okay, so I just wanted to go ahead and show you guys that, and this explains why with NBS, we're going to get a reaction at that allylic position, because this guy is nice and stable. And actually, I should be pointing here with NBS because it's actually a radical mechanism, so it happens there. But anyway, yeah, so that's the stability of these conjugated systems. And let me just end by going back to the previous page here and just sort of focusing on this guy, because this is going to be similar to some of the molecular orbital energy diagrams that we'll do later on in the next chapter. Maybe later in this chapter, we'll see. So just focus on the parts here. We've got our energy axis. We've got our 4 molecular orbitals that came from 4 atomic orbitals. And then I draw out my individual atomic orbitals. And I color in the phases. When everything's the same phase, that's our lowest energy. When I've got one node, one place where the phases switch, that's my next highest. Next one up has 2 nodes, and then 3 nodes. If I had a triene instead of a diene, and I had 3 double bonds and 6 carbon atoms with 6 p orbitals, I would have 2 more sets of blobs here, and I'd have another 2 orbitals. And you can draw these if you want. They take a little bit of time. But anyway, go ahead, watch this again, because I know that molecular orbitals can be a little bit tricky. And in the next lecture, we'll go ahead and take a look at some reactions and reaction mechanisms. And just keep this in the back of your mind as to why conjugate dienes are stable. Remember, it's molecular orbitals can help explain that. All right. Until next time, stay safe out there. Bye now.